Hi. So in today's video, we will be looking at how to do a titration of a weak acid with a strong base. So our question is, consider the titration of 35 milliliters of 0.02 molar acetic acid with 0.1 molar sodium hydroxide, and the Ka of acetic acid is 1.8 times 10 to the negative 5. So today we will be looking at how to calculate the pH initially in the flask, how to calculate the pH before our equivalence point, how to calculate our equivalence point and the pH at the equivalence point, and finally we'll be looking at how to calculate the pH after the equivalence point. And then we will look at the titration curve for a weak acid strong base titration. So our first question is, what is the original pH in the flask? So we had 35 milliliters of 0.02 molar acetic acid in our flask. So all that's in the flask is a weak acid, which is acetic acid. So we will start by using a rice table because we're going to be calculating the pH of a weak acid. And as you know, the reaction of a weak acid is going to be HA, and it's going to turn to H plus A minus. We'll be using a generic reaction so that you can use this for any type of questions you get as well. So what is our initial amount? Well, since we're working with a weak acid alone right now and the volume is constant in the flask, we don't need to use moles, so we can just use molarity. So the molarity of our acetic acid is 0.02 molar. We have 0 protons and 0 of the acetate anion in our solution currently. So our change will be minus X for HA because it's going to dissociate into H plus and A minus. So we will gain some of those protons and some acetate in our flask. So our equilibrium value is 0.02 minus X, X, and X. So what do we do at this point? Since it's a weak acid, we use the Ka expression. Ka is equal to H plus times A minus all over HA. And we know our values of H plus and acetate is X multiplied by X all over 0.02 minus X. And that's equal to X squared over 0.02 minus X. That's equal to our Ka of acetic acid, which we said was 1.8 times 10 to the negative 5. So our next step is to solve for X. And again, what will X give us? X will give us the concentration of our protons. So if we do the negative log of X, we should get our pH. Alright. So again, when we're trying to solve for X, we can use two different methods. We can use the quadratic formula or the approximation. We'll start with the approximation, and if it's not less than 1%, then we're going to use the quadratic formula. So X squared over 0.02 is equal to 1.8 times 10 to the negative 5. This is the approximation method because we're going to be ignoring X in the denominator, and if we do that, we get a value of X equal to 6 times 10 to the negative 4. So let's check if this value is less than 1% of original concentration. We do 6 times 10 to the negative 4 divided by original concentration, which is 0.02, multiplied by 100%. We get a value of 3%. And since this is greater than 1%, we cannot approximate X is equal to 0 in our denominator. So what we have to do is we have to use the quadratic formula to find our X value. So again, X squared over 0.02 minus X will equal 1.8 times 10 to the negative 5. If we rearrange this equation, we're going to get X squared is equal to 3.6 times 10 to the negative 7 minus 1.8 times 10 to the negative 5 X. We can further change this equation so that it's X squared plus 1.8 times 10 to the negative 5 X minus 3.6 times 10 to the negative 7. We set that equal to 0. Now we can set up our quadratic formula. X will be equal to negative 1.8 times 10 to the negative 5 plus or minus the square root of 1.8 times 10 to the negative 5 squared minus 4a. Our C value will be negative 3.6 times 10 to the negative 7. And all of this will be divided by 2a, which would be 2 times 1. And we get our positive x value as 5.91 times 10 to the negative 4. So this is the concentration of our protons in our flask when there's only acetic acid. So next we have to find is the pH, which will be the negative log of our x value. So the negative log of 5.91 times 10 to the negative 4 gives us a final pH value of 3.22. So the pH initially, when there's only acetic acid in the flask, is 3.22. And this makes sense because we have a weak acid, so our pH should be low. Okay, let's look at our next question. What is the pH after the addition of 3.5 milliliters of 0.1 molar sodium hydroxide in the flask? So this is where the titration begins, and we'll be trying to find the pH before our equivalence point. So the first step to do is to figure out how many moles of sodium hydroxide and how many moles of acetic acid we have in our flask. So to get the moles of sodium hydroxide, we just have to multiply the volume times the molarity. So 0.0035 liters, which is 3.5 milliliters, times 0.1 molar will give us a final value of 3.5 times 10 to the negative 4 moles sodium hydroxide. And how many moles of acetic acid do we have in our flask? Well, from the very first slide, we said we had 0.035 or 35 milliliters of acetic acid, and its concentration was 0.02 moles per liter. And that gives us a value of 7 times 10 to the negative 4 moles acetic acid, which we will write as HA. So the next thing to do is to do our Rice table to see what reaction is going on in our flask. So we know we have to react our acetic acid with our NaOH, and that will give us our NaA, which is our sodium acetate, and water. So we will be using moles as our initial amounts instead of molarity, because now we have a reaction and our volume has been changed. So the initial mole amount of our acetic acid is 7 times 10 to the negative 4. Our initial mole amount of sodium hydroxide is 3.5 times 10 to the negative 4. We have no acetate or water in our solution right now. So the change is simply all the sodium hydroxide is going to be used up and going to react with all of the acetic acid that we have. So we're going to lose all the sodium hydroxide on both parts, and we would gain that on our right hand side. Our final value of our acetic acid would be 3.5 times 10 to the negative 4, 0 amount of sodium hydroxide, and then we'd have 3.5 times 10 to the negative 4. And we would have 3.5 times 10 to the negative 4 moles, again these are moles, of acetic acid and acetate in our flask. And we'll be ignoring water because it's not going to affect our pH. So how are we going to find the pH now? Well, we have acetate, or right here it's labeled as sodium acetate, and we have our acetic acid. So we have a conjugate acid-base pair existing in our solution. And what does that mean? Well, that means we have a buffer solution. So since we have HA and A minus in our flask, we have a buffer. And again, how do we find the pH of our buffer? Well, that's where we use the Henderson-Hasselbalch equation. Henderson-Hasselbalch equation, well, that is pH is equal to pKa plus log the concentration over A minus, or the mole amount, the concentration or the mole amount over HA. So we calculated what A minus and HA was just now. So all we have to do is fill in the rest. So our pH is going to be equal to pKa. What is the pKa? It's going to be the negative log of our Ka value, which is 1.8 times 10 to the negative 5. And our log, we said our value of A minus was 3.5 times 10 to the negative 4 moles over 3.5 times 10 to the negative 4 moles of HA. Moles are going to cancel out. This value here will become 1 because it's the same number on the numerator and the denominator. So the log of 1 is going to equal 0. So all we're going to have left is our pH is going to be equal to our pKa. And we get a pH of 4.74. So after the addition of 3.5 milliliters of 0.1 molar NaOH to our flask, our pH is 4.74. And it's also important to realize whenever pH equals pKa, we are at the 1/2 equivalence point volume. So our next question is, what is the equivalence point volume and what is the pH at this point? Well, our last question, our volume that we added was 3.5 milliliters of sodium hydroxide, and that was the 1/2 equivalence point. So to get the equivalence point, all we have to do is multiply that by 2. So 3.5 milliliters times 2 would equal 7 milliliters. So we know if you add 7 milliliters of sodium hydroxide, you'll be at your equivalence point. But what's another way of calculating that? Another way of calculating that is M1V1 is equal to M2V2, where M1 is the concentration of acetic acid, V1 is the volume of acetic acid in the flask, and M2 is the concentration of our sodium hydroxide, and V2 is the equivalence point volume. So if we fill in the values, 0.02 molar for acetic acid, and we have 0.035 liters of acetic acid, and that's going to be equal to 0.1 molar of sodium hydroxide, and V2s are unknown. If we simply divide both sides by 0.1, we will get our V2, and that would be equal to a value of 7, or 7 milliliters, which is going to be 0.007 liters. So the equivalence point volume, again, another way of calculating it is M1V1 equals M2V2, and that will give us a value of 7 milliliters. So the next question is, what is the pH at this point? So when we've added 7 milliliters of sodium hydroxide, what is the pH? First, let's figure out how many moles we have of acetic acid and how many moles we have of NaOH. So like the last question, we said we have 7 times 10 to the negative 4 moles of acetic acid in the flask. That value won't change. But this time, the moles of NaOH added will be different. We'll be adding 0.007 liters times 0.1 molar of NaOH, and that will give us a value of 7 times 10 to the negative 4 moles of NaOH. And you can see that this is why it's the equivalence point volume, because the moles of NaOH added will be equal to the moles of acetic acid in the flask. So, as usual, our next step is to do a rise table to visualize the reaction going on. So again, our reaction will be HA plus NaOH is going to create sodium acetate and water. So our initial amount of HA, we said that's 7 times 10 to the negative 4 moles, and that's the same thing as our NaOH because we were at our equivalence point. We have 0 amount of sodium acetate, and we don't have to consider water because it's not going to affect our pH. So this reaction will occur, and all the sodium hydroxide is going to react with the acetic acid. So we're going to lose all of that on both sides. And we will gain that exact amount on the right hand side because all of that has reacted to create sodium acetate. So we can see here that the only thing left in our flask that can affect our pH is sodium acetate. And again, sodium acetate is simply just acetate in our solution. So let's try to figure out the concentration of our acetate ion. We know we have 7 times 10 to the negative 4 moles of it in our flask. And we know the volume of our flask is 0.035, which was 35 milliliters that was initially in the flask. And we added just now 0.007 liters of NaOH. This will give us a concentration of 0.01667 molar. So we have 0.0166 molar of acetate. Our next thing is to figure out what is the pH of this weak base. So it's very similar to the calculation that we did at the beginning of this video, which was calculating the pH of the initial flask. This time we'll be calculating the pH of a weak base because all we have is a weak base in our solution when we're at this equivalence point. So we can set up a Rice table and look at a reaction. A minus, our weak base, is going to react with our water, and it will create HA and OH minus. We know that our initial molar amount is 0.01667 molarity. The reason we're not using moles now in a Rice table is, again, all we have is a weak base, and we're not having a reaction going on, and our volume is staying constant, so we can use molarity. We don't have to consider water as affecting our pH, and we know that we have 0 amounts of HA and OH minus in our flask at that moment. So what's the change that's going to happen? Well, A minus is going to react with water, so you're going to lose a little bit of your A minus. You're going to gain that as HA and hydroxide. So equilibrium values would be 0.01667 minus X, XHA, and XOH minus that was created. So the next thing we have to do is figure out the pH of our weak base. So to figure that out, we need our Kb expression, since we're working with a weak base. And so our Kb expression is HA, which is the products, multiplied by OH minus, divided by the reactants, which is just A minus. So we said this would be X multiplied by X all over 0.01667 minus X. And we said that's equal to our Kb. And what is our Kb value? Well, we were given our Ka value in our initial question, and we said our Ka is equal to 1.8 times 10 to the negative 5. But we weren't given our Kb, which was the equilibrium expression for acetate. So how do we calculate that? Well, from our weak acid base equilibrium video, we know we can solve for Kb by doing Kw divided by Ka. So 1 times 10 to the negative 14, which is our Kw value, divided by 1.8 times 10 to the negative 5, will give us a value of 5.56 times 10 to the negative 10. So we know that our Kb value is 5.56 times 10 to the negative 10. And so all we have to do is solve for X. But this time, X is not giving us our H plus value, it's going to be giving us our OH minus value. So if we do the negative log of our X, we'll be getting our POH, so we have to do 14 minus that to get our pH. So again, there's two ways we solve for X. One's the approximation method, and if that doesn't work, we'll go to our quadratic formula. So using the approximation method, X squared over 0.01667 should be equal to 5.56 times 10 to the negative 10. If we solve for X, we get X equal to 3.04 times 10 to the negative 6. So let's check if this works. To check if it works, we do our X value divided by our initial concentration, which is 0.1667 molar of our weak base. We're going to multiply this by 100%. We get a value of 0.018%. And this is much less than 1%, so we can use the approximation value, and that means that the X value we calculated is accurate. So the negative log of our X, like we said, is our POH. And that would be the negative log of 3.04 times 10 to the negative 6, which is equal to 5.51. To get the pH, we just do 14 minus POH. So we get the pH equal to 14 minus 5.51, which is equal to 8.49. So what we're saying is, at the equivalence point volume, all of our weak acid reacted with our strong base, which was sodium hydroxide, and all we were left with was our weak base left in our flask. And so the pH of our weak base is 8.49, and this makes sense because a weak base has a high pH, but not a very high pH. Alright, let's look at the last question. What is the pH after the addition of 10 milliliters of 0.1 molar NaOH? So we know we're past our equivalence point now, so that means we're going to have excess sodium hydroxide being added to our flask. So first thing we need to do is calculate the moles of sodium hydroxide being added. Well, we have 0.01 liters of sodium hydroxide multiplied by 0.1 molar sodium hydroxide. and that will be equal to a value of 0.001 moles NaOH. And we know that our flask initially had 7 times 10 to the negative 4 moles of acetic acid, which again we're labeling as H8. So if we make our rise table, we have the same reaction. And our initial amounts is 7 times 10 to the negative 4 moles, 0.001 moles of sodium hydroxide being added, and we have no sodium acetate or water yet. Our change, well, this time all of the acetic acid will react with our strong base, so we'll be losing all of that. And we would be gaining that exact amount on the other side. So what would our equilibrium values be? Well, all of our acetic acid was used up, so we have none of that left. We would have excess sodium hydroxide left over, 3 times 10 to the negative 4 moles of sodium hydroxide left. And we would also have 7 times 10 to the negative 4 moles of sodium acetate. Since we're past our equivalence point and we have excess strong acid, we don't have to consider the effect of acetate on our pH, because the strong acid is going to be far more significant than the value of our sodium acetate. So we're not going to consider it. All we have to consider is that we have 3 times 10 to the negative 4 moles of sodium hydroxide. So let's calculate the concentration of our sodium hydroxide, and more specifically the hydroxide anion. Again, since it fully dissociates, it's a strong base, we can calculate the concentration of our sodium hydroxide and say that's equal to the concentration of our hydroxide ion. So we have 3 times 10 to the negative 4 moles of hydroxide, and our volume was, well, initially we had 0.035 liters of acetic acid, and we just added 0.01 liters of sodium hydroxide, and that will give us a final concentration of 0.00667 molar of hydroxide. So how do we calculate our pH? All we have to do is the negative log of our OH value, and then 14 minus that will give us our pH. So the negative log of 0.006667 gives us a pH of 2.17. So our pH would be 14 minus 2.17. This gives us a value of 11.83. So we can see now that we have an excess amount of sodium hydroxide, we have a very strong base left in our flask. So our pH is going to be much higher than at the equivalence point. It's going to sharply increase because now we have a strong base, and the contribution of a strong base to the pH is very significant. So now that we have looked at all of the different calculations, let's look at our weak acid with a strong base titration curve. We can see that our curve begins at a very low pH because all we have here is our acetic acid. And slowly we're going to start adding a small amount of sodium hydroxide. And you can see here, this is where our pH will equal to pKa because we're at 1/2 the equivalence point. So we can see our equivalence volume is 10 milliliters in this example. So at 5 milliliters, we can see that our pH will equal our pKa for a weak acid with a strong base titration curve. And as we pass our equivalence point, we have an excess amount of OH. So that's why our pH will sharply increase. So it's important to realize that your pH will sharply increase after your equivalence point because we're going to have excess hydroxides. From here to here, we can see we're in the buffer range. So this is where we have a buffer solution where all of our sodium hydroxide has been used up and we have acetic acid and acetate in our solution. So we have a conjugate acid and a conjugate base pair existing, and that's why we have a buffer solution. And you can see that's also why the pH doesn't change very drastically in this region. So if you enjoyed this video, make sure to leave a comment, subscribe, drop a like, and have a good day.